And okay, let's do this again. Okay. Okay, any questions about this part? I hope it is clear because I tried to link this our real business to the binomial. Why we use binomial to handle this problem? Because this is a classical binomial, not binomial issue, right? So we have two categories here. All right. We have two outcomes actually. One is the parental type, which refer to the no crossover, and one is the non-parental type, which refers to the crossover. All right. Okay, then we use this simple example to show how the tossing coin is kind of like equivalent to what we do for this backcross design. Okay, now so this part is important. So it's very likely. The probability is very high. You see some questions related to this one in your exam. Oops. Okay, so so I gave you some link. One of those links is about like the information about the binomial, right? Binomial distribution. All right, this is how we define the binomial distribution. So suppose X is a random variable follows a binomial distribution. So and this is the probability density function. So let me show you how we understand this. So probably some of you already knew this because if you took statistics class, so definitely you're gonna learn this. So this is the density function, and here, oops. What's this? Okay, so here the P is the only parameter for this binomial distribution, and the number of this P is unknown. So our goal is to estimate this parameter, right? We want to estimate this this parameter for this model. We knew this is a binomial, but we don't know this parameter. Just like the backcross design. So we knew this is a backcross, and we knew there are two categories: parental type and the non-parental type of progeny. But we do not know what for our business. In our project, what is the unknown parameter, and we want to estimate that. It's R, right? R is the parameter that we are interested in, and we want to use our data to estimate this R. Actually, that R is equivalent to this P, because R is a probability to having a crossover, and here P represents the probability of being a successful outcome. So talking about like tossing a coin, so we can define this P as the probability for a head showing up, right? Does that make sense? Any questions? So here we want to estimate this. We don't know this. So what we do is like, okay, we toss a coin. So now let me still use this example. We toss a coin for n times. So the n here is the size of the experiment. Why n must be a large number? So can n be 1? No. So if you toss a coin just one time, you don't know if this coin is a fair one or not, right? But if you toss the coin for multiple times, let's say 10 times, and based on outcome, you can easily tell how likely this coin is a fair one. So this is equivalent to tell people, okay, how likely the probability, the P, the parameter P is equal to 0.5, right? Does that make sense? So if this coin is a fair one, so you can easily tell people, okay, the parameter P is likely to be 0.5, right? All right, so this is what we want to do. Okay, so the N here is the experimental size, and the K is the outcome. So here, K is like the X. So K means like out of this 10 tosses, how many successes do you observe? How many heads do you observe? So for example, if this is the experiment, P is unknown, and we only observed K out of this N. So we can use binomial, this probability density function to calculate the probability for this observation. So this is how we calculate this. So here, because we have like K times of success, so we got this P to the power of K, because each time we have the P, we have the probability of P to showing a success, right? So since we got K times, so that's the joint probability for observing K independent successes. All right. And also we other than the success, we also see some failures here, right? The number of the failures equals to N minus K. And the probability for each failure is 1 minus P, reciprocal. So I remember Mariano asked this reciprocal question last time, right? This is why the P and the 1 minus P is reciprocal. They must add up to 1. So this is the joint probability for seeing K success and N minus K failures. However, because there are many ways, so if this is the 10 tosses here, there are many ways to put this K success, right? Let's say K equals 5. You could have like first 5 are success and the next 5 are the failure, or you can get like the first one is success, the second one is, so different ways. We call this combination. So that's why you see these factors here. Does that make sense? So the whole thing is actually the probability of seeing K success out of this N. So this is exactly what we do here, right? So back to our business, we got this many progeny from this backcross. We see N1 plus N2, N4. So that's the parental type, right? We see this many like success, let's say this is the failures. If there's no crossover, we say this is failure, right? So this number is associated with the probability 1 minus R, right? Okay, now still out of this N progeny, we got this, the second category plus the third category. That's for another outcome, right? The success. And the success probability equals to R, the crossover. Do you see the similarity between these two situations? Okay, very good. Any questions before I move forward? Now the important part comes, all right? All right, since we knew this is the probability for this outcome, and we want to estimate this. All right, because when we do an experiment, we got this data, right? Which means this data has a big chance, has a very large, big probability to show up, right? So because there are all different kind of like outcomes. Why this one showing up in your experiment? Because this outcome is quite likely to occur. Do you agree? So that's why we try to find the optimal, the best value for P to maximize this probability density. Does that make sense? All right. So this is called the maximum likelihood estimation. And because if you look at this formula, this part is data, it will not change because this is what you observed. So this will not contribute anything about making this entire term the maximum. Only this part, look at here, which involves the unknown parameter P. So this part can be maximized, right? So, all right. So what we do here is try to maximize this part by finding the optimal estimation of P. Does that make sense? For this week and next week, I try to move very slowly because I want to help settle like the solid foundation for everyone. But in the future, once you feel very comfortable with everything, we could move very fast. And any questions here? This is very basic, but very, very important. Here, I try to give you some like concepts, some like idea about statistics and how we use the boring statistical models to help us solve our like funny, interesting biological questions. All right. Okay, since we want to, okay, we only took this part out. See, because we want to maximize this, right? By finding the best P estimation to maximize this, we call this likelihood. We use L to represent this part, and we want to maximize this. As I mentioned last time, because this is this formula takes a form of product. So it's a headache. It's so difficult to deal with this product and the power series. So then we use a very clever way. So we just take the log for this likelihood, because there's a I forgot the term mono. So the relationship between the likelihood and the log likelihood is something like the what is the term? Mono. Totally forgot. So Mariano, can you help me? So if you want to see like increase.
I know what you're referring to, but I forget. Yeah.
Yeah, sorry about this. So here I want to say like the relationship between likelihood and the log likelihood is like, so if one thing is increasing, the other thing is also increasing, never decrease. So let me find this. So I didn't hear you very clearly. So you also forgot about that term, right?
Yeah, but I know what you're talking about.
Yes. Okay. Give me a second. Let me find out that one. So that's important. Sorry. Sometimes like some words just slip from my mind.
Uniform.
Oh, monotonic. Sorry, monotonic English. Yeah, monotonic. Yeah, English is a hard language.
Yeah,
so difficult.
it is.
So it's difficult for. So I think my job is kind of like hard because it's like a combination of math, statistics, genetics, and biology. So sometimes I have to learn a lot of like vocabulary, including statistics and biology. All right. Okay.
We thank you, Dr. Jia.
Thank you. All right. Monotonic increase. So that's why the reason why is that is like since the relationship between the likelihood and the log likelihood is the monotonic increase. So if we want to maximize this guy, so instead we can maximize this guy, right? So that's the same. So we take a log, and what a beautiful thing it becomes, right? So instead of dealing with this like product power stuff, we deal with like the sum, right? And this is easy. So how do we maximize this? So this actually, as I showed you last time, so the distribution, when you take different p value, the value for p, so the x-axis is the p. Here the p can take different values, right? If you use different, if p takes different value, you're gonna get different log likelihood here. All right. And some are low, some are high. And okay, then we need to find the best p, the p hat, which is the best value for the p that can maximize this curve, right? The likelihood, the log likelihood. So this is what we have learned before, either in the high school or in the college. I think in the college math. So the professors also talk about this. This is the basic strategy. All right, then to achieve this, we just simply, so I'm going to write something here. So we're going to do the first derivative for this guy. And this part is important. I may ask you similar questions in the final exam. So we do this in terms of P, right? We do the first derivative. And the first part is very easy. So it becomes K divided by P, right? It's very easy. But the second term will become what? Will become, because this is a minus P, so we put a minus here, multiply by this. And the numerator is N minus K. And the denominator is 1 minus P, right? Okay, then if you simplify this, it will become K over P minus 1 minus P and minus K, okay? So this is the first derivative. And if we want to find the p-value, we have to set this equal to 0, right? I put this sign here. So we purposely put this formula equals to 0. And then we solve this. Let's solve this. All right. So this means like the K, if you move this part, see this part to the right-hand side, you will get this, the K over P equals to N minus K and 1 minus P. Then the next step is easy. So you just simply cross product, right? Cross product. And this will gives you what? You can solve this by yourself. This is an easy practice. And this will gives you the P hat. The best p-value equals to K divided by N. Yeah, the job is done. Does that make sense? Okay, so this is why, in the binomial distribution. So if we got the experiment data like this, so this is the best way. This is the best way to estimate your unknown parameter P, which is defined by this ratio. So the numerator is the number of successes, right? And the denominator is the total number of trials. This is your data, and you successfully use your data to estimate the parameter of interest, MLE. So this is MLE. All right, okay. Can we move forward? Do you need time to write this down? Okay, good. All right, let me erase this. Okay, so if you are comfortable with this, then I think you must be very comfortable with this, all right? Okay, so here, binomial, this is from our experiment, okay? So our experiment, we generate 4 categories, right? 1, 2, 3, 4. I use this yellow to represent one outcome, which is the parental type. And I use the pink to represent the other 2, which means the non-parental type. So although we have 4 genotypes, but indeed we have only 2 outcomes, either the parental type or non-parental type, right? So then we can use the binomial. So this part is the constant factor we don't worry about. The only part is here. So we want to maximize this part, right? This is the thing we want to maximize. And sorry, this is a typo. So I copy and paste from the textbook. The textbook has a typo, so I cannot make change. So so thank you. Let me see.
It was Andrea who noticed it.
Oh, Andrea, yeah, Andreas, yeah, thank you, Andrea. The last time you told me about this. Yeah, okay, thank you. So yeah, please pay attention. So this is a typo. So okay, anyhow, so we want to maximize this. This is the likelihood, right? Because this is ugly, so we don't want to deal with this. So we just take a log likelihood because they are monotonic increase. So instead of maximizing this, we can maximize this. And this is beautiful, just like this. And now we take the first derivative and set this guy to 0. When you solve this, this is like this. This is equivalent. This is equivalent to this. Do you agree? So now I think I made it clear like why we use binomial distribution here to help us with our backcross design. Any questions here? Very good. Okay, let's move forward. Okay, so yeah, so this is how we do this, right? Because if you take different value for the p, you're gonna get a different the log likelihood value until you get here, right? So here the first derivative equals to 0, and this is what you want to find. And the value here gives you the best estimation for the unknown parameter. Okay. All right, this part is a little bit like advanced because so I would rather like be slow here a little bit, slow down here. So in the past, when you took some like a statistic class, so I believe your professor have told you the big goal for any statistical analysis is to estimate an unknown parameter, right? So for example, here we want to estimate the unknown R, which is so don't forget about R. So here, our business is to calculate this R, to estimate this R, and this represents what? The genetic distance between two genes. All right, once you got the best value, best estimation for this guy, so you also need to, when you report your results, you also need to report this thing. What is this thing? This is the standard error. So you must let people know, okay, I can give you the best estimation of this parameter, but this is not always true. I'm going to give you something like the confidence interval, plus and minus some standard error here, right? This is kind of like confidence interval. So we want to give people like this, and we will let people know, okay, so even if this is not the correct answer, but the real value for this R is highly likely to fall in this region. So this is the confidence interval. This is the center, which is the estimation. And we give this estimation a buffer region, right? A buffer region, and the real value has a very high likelihood to fall in this region. So this is what we want to report in any statistical analysis, right? So how can we get this, right? If we need to do this, we need to know how to do this, right? And this is one thing. So when you report your results, give the point estimation and give a range. So this is the range. And also this can help us. So if you have a range like this, this range can help us to form a hypothesis testing. Because for example, if you estimated your R equals to 0.4, can anyone tell me what does that mean? If you R, so R here represents the genetic distance between A and B. And based on your backcross experimental data, you can give the best estimation for this R equals to 0.4. What does that mean?
They're on the same chromosome?
Yes, and and it kind of like this R is close to 0.5, so you cannot say, okay, this is a tight link, right? Probably it's a very loose link, and since this is a loose, it could be like although these two loci are on the same chromosome, it could be like they behave when during the meiosis, these two genes could segregate totally independently, right? Since this value is very large, close to 0.5, and you want to test if this linkage between A and B is significant or not. So you can do a test. So which means like you can test this R equals to 0.5, or this is our non-hypothesis. Our non-hypothesis is we want to test this R, if this R equals to 0.5, or alternative hypothesis, this R makes sense, is significantly less than 0.5, which indicates a linkage between A and B. Does that make sense? So we use this interval or confidence interval or the standard error or whatever to help us to form a hypothesis testing. Okay. All right. Can I erase those? Any questions?
Can you explain again why you set the null and alternative hypothesis based on 0.5?
Oh, yes. Okay. So yeah. Okay. I will talk. So I will give you some like idea now, but later on, I will show you example, beautiful example to see why we set up the two competing hypotheses like this. All right. So so usually we so during any hypothesis testing, we have two competing hypotheses. Here, one is this, and the other one is this, right? So why we always put like the R hat equals to 0.5, the easy one in the non-hypothesis, because this one you can easily construct a test statistic to calculate the p-value. So that's why we always put the easy one in the non-hypothesis, and we always put the non-hypothesis on the test. We do not test the alternative hypothesis. So once you test the non-hypothesis, which means in our case, which means like there's no linkage, right, between A and B. So if your data support this non-hypothesis, we just take this non-hypothesis. We believe these two genes are either unlinked or even they are on the same chromosome. They are far removed from each other, so they behave like two independent genes. So that's what we can do. However, if your data does not support non-hypothesis, then the next step, you're going to reject your non-hypothesis. You're going to just take the alternative hypothesis as true. And this means these two genes are not independent. They, during the meiosis, they are on the same chromosome. And during the meiosis, they likely like assort dependently, right? So this is what we do. Any questions? Okay, so yeah, don't worry. I'm gonna give you an example to show how we understand the whole process. Okay. So first, we need to focus on this. So we know how to estimate this, right? So we use MLE to estimate the R hat, the unknown parameter. And then we need to know how to estimate this standard error. Standard error means the measurement. So the error for the estimation of this parameter. Okay, so do you still remember this? What is this? This part? We call this the score function. Let me go back to the previous slides. So the first derivative is called the score function. The first derivative in terms of the log likelihood function, right? Okay. Now, if we take the second derivative, then we call this is the h function here. Okay. So the h function is actually is equivalent to take another derivative, the second derivative of the log likelihood, right? And so if the first derivative function, which is the score function, is try to find the position where this curve has a zero slope, right? And the second derivative function, actually h function, is try to see how fast this slope can change. So let me show you example here. So I give you two estimations. So for the first one, you got a likelihood like this. And this is your estimation. The slope, the zero slope, right? And this is your estimation here, the p-value. The second one, let's use this, is more sharp. And okay, for this one, this is the place you got the estimation which achieved the zero slope. So this represents your estimation of the p-value. Which one do you think will provide a more accurate estimation? Of course, the second one, right? Yeah, because the second derivative here actually measures how fast this slope change along at this point along this curve. So which means at this point, this slope change faster than here, right? Along this curve at this point. So if you read your textbook, it gives you more information about this, the second derivative. And actually, as I mentioned, actually this second derivative or the h function gives you some idea about how fast this slope change. And if you take the expectation, the minus expectation of this h function, this gives you the information function. The information function, which is invented by Fisher. So actually, we call this Fisher's information. It is a way of measuring the amount of information that an observed random variable x. Here, x means the number of success. So we want to use this information to measure the amount of information that this random variable carries about unknown parameters. So here we want to estimate R, right? We use the number of the number of the progeny in the recombinant category, and what the data there can carry about the information about the unknown parameter R here. So this is the information, and if we take the reciprocal, the 1 over the information function, that gives us the variance. So everybody knows the variance, right? If you take the square root of the variance, this gives you the standard error. So something like this. So basically, we use the second derivative and to generate the information function, and use the information function to estimate the variance and the standard deviation. Yeah, this is too complicated. I will not put any questions about this on the final exam, but just for your information. So here we try to report this, and we're going to use this to perform a hypothesis testing. For what? We want to perform a hypothesis testing to test what? Can anyone tell me? We want to test whether this estimated R equals to 0.5 or not, right?
Yes.
Yeah, so this, in another way, we want to test the linkage between A and B is significant or not based on our experimental data. So this is what we do here. I hope like I give you this some idea so you can understand what is going on by doing the genetic mapping. So yeah, so in breeding, so we try to find if these two good genes, I mean, for each gene, there's different alleles. If these two genes are tightly linked, then this can help us. Like, so for example, if there's a parent with both good alleles in this parent, so we use, but for another parent, although the genotype is the same, but the face, the good alleles are not on the same parental chromosome. So in this case, you know which one you're gonna choose for breeding the next generation, right? Because the linkage means like the good alleles together is more easily likely to be passed on to the next generation and next generation. So this is why we want to test the linkage between any two genes of interest. Okay, so yeah, here we want to test the linkage. As I mentioned, there are different ways to set up a test, but the most efficient way, common way we do is like we put the easy way in the null hypothesis. We just test the null hypothesis. We don't touch the alternative hypothesis. So once we construct a test statistic to test the null hypothesis, we either accept this one if the p-value is greater than 0.05, right? This is what we do in the past. However, if the p-value calculated based on testing the null hypothesis is super low, for example, it's 10 to the minus like 6, 0.0001 or something like that, which means it is very unlikely that your null hypothesis is true. Then we're gonna reject our null hypothesis, and we just take the alternative hypothesis as a true conclusion for free. Okay. All right. Okay, as I mentioned, so it's important to construct a confidence interval, right? This is the R hat. So based on our calculation, we can get this R, and we can also calculate the standard error for this one. Then we can easily form a non-distribution and a confidence interval. And we're going to use this for a test. All right. So this is our non-distribution, the non-distribution. Based on our null hypothesis, we can draw a non-distribution for the parameter of interest. And now you can easily calculate a test statistic based on your data. And then you compare your test statistic against this non-distribution. So if your test statistic is around here within this range, which means like, yeah, it's fairly reasonable if your null hypothesis is true. So you got this value of the test statistic is very reasonable. So in this case, we accept our null hypothesis. However, if you calculate the test statistic based on your data, and this test statistic is kind of like extreme, either extremely low for out of this region, right? This is the region we want to test. Or if you got a test statistic which is standing in another extreme area like this, extremely large or extremely low, which means given the null hypothesis, it's very unlikely for you to see a test this statistic like this big or like this small. So in this case, we are going to reject the null hypothesis and take the alternative hypothesis, right? Okay. So this is my favorite part. I'm going to show you. So what we do for the hypothesis testing is like this. So it's just like what is going on in a court in this country. So so we put this. So for, let me see. Oops. Can you see my screen here?
Yes.
Oh, okay. Okay, good. All right. So suppose we have a we have two hypotheses, competing hypotheses here. And in this court, the null hypothesis is always like we assume this guy is innocent. So the null hypothesis. Why not? I cannot do this. Let me try this again. Sorry, there's some problem, technical problem with my Where's my screen? Okay. All right. So the null hypothesis is the innocent. Okay. Innocent. All right. Then when we knew, like, if we want to do a hypothesis testing, there must be another competing hypothesis, which means it's guilty, right? Okay. We have two hypotheses here, but we only put this one, the null hypothesis, on a trial. So given this null hypothesis, or by assuming this guy is innocent, then we have a model, right? From that model, we just collect the data. So we try to collect the data to support that non-model by which the null hypothesis is true. All right. So once we got the data, we can do the data analysis. So we can calculate the test statistic. The collecting data is actually the sampling process. So it's something like when you have a design, so you do the back cross or test cross, you got your data, and then we can test our data, so to see how likely the data is supporting our non-model or non-hypothesis. If the p-value, so we're going to talk about this, if the p-value is large, greater than 0.05, and which means like your test statistic falls into the region in the middle, right? The non-distribution. Then we believe we accept the non-hypothesis. And we believe this guy is innocent, so we set him free. However, on the other hand, if the p-value calculated from your test statistic is extremely low, like less than 0.05, in other words, so your data does not support your non-model or non-hypothesis, you're gonna reject the non-hypothesis and take the alternative hypothesis. You're gonna put this guy in the jail. So this is exactly what we are doing for a hypothesis testing. So here, by doing the linkage test, we treat the non-hypothesis as there's no linkage. So R equals to 0.5. So here is R, right? R equals low linkage. And the alternative hypothesis means like R is less than 0.5, means they are linked, the two genes. All right, then based on the null hypothesis, low linkage, so we collect data and we calculate the p-value. Then we have two possible outcomes. Either we accept the null hypothesis. Null hypothesis means like these two loci are independent, they are unlinked, or they're linked. So when you reject the null hypothesis, which means like there's a strong evidence to show a significant association between these two loci. All right, remember, we only test one hypothesis, right? The non-hypothesis. This is another example to show this. So suppose you're going to a party tonight, and after work, and you want to become the focus of the party tonight. So after work, so you rush into a department store. You really do not have a lot of time to try everything on, right? So now you just look at the all possible addresses, and you found two. You found two, which could make you the focus of tonight's party. So let's say. Oops. So yourself is the data. Yourself is the data, and you have two hypotheses. You have two dresses from which you're going to pick one to go to the party, and so you really do not have enough time to try both. Then you just put one on. So that one is the non-hypothesis. The other one, yeah, is an option. So you put the rest on yourself, which means the fitting the data with the non-model. Yeah, you look into the mirror to see if it fits you or not. If you see a lot of like rooms between you and the dress, that means like that dress doesn't fit you very well, right? In that case, you're going to get a very small p-value, which will make you to reject the null hypothesis. So if that is the case, you just throw this dress away and took that one and go to the party. If when you look at the look into the mirror and see the dress fits you very well, and there's no little room between you and the dress, then you believe this is the one, and you don't just leave that one and take this one and go to the party. So this is what we do for the hypothesis testing. And the p-value, as I mentioned, is equivalent, in this case, is equivalent to the probability to become the focus of the party if you put on this one. Any questions here? Okay, now you understand, right? So for any hypothesis testing, we have two competing hypotheses, but we don't test both of them. So we just test the non-hypothesis, and then we can calculate the test statistic and the p-value. And with the p-value, we can easily either accept the non-hypothesis or we reject the non-hypothesis, but take the alternative hypothesis. Any questions here? Okay. All right, the same thing here, right? So when we do the hypothesis testing, we have two distributions. One is the non-distribution for non-hypothesis, and the other one is the alternative distribution, which is based on the alternative distribution. We only test this one and give us the answer, right? Okay, the same thing here. So I give you, so in this example, let's say we want to test whether this coin is a fair one. So this is the scientific question we try to address, right? In the future, when you do any project, your own dissertation project, for any project, there must be a core question to be addressed, right? So from that question, you can form two hypotheses, either yes or no. So this is what we do for scientific research. All right, so this is the question we want to address, scientific question. And based on this, we have two competing hypotheses. And then we, based on that, we can easily construct our experiment and calculate our test statistics and calculate the p-value. And with the p-value, we can answer this question. Just treat this question as your dissertation project question. Yeah, then congratulations, you're gonna graduate in 4 or 5 years. Yeah, okay. So this is what we do. So for example, okay, now we always assume the non-hypothesis is true. And given this non-hypothesis, we can easily get the parameter equals to 0.5, right? Here we only have one parameter here, which means that the probability of being success or the head. All right. And if this is the non-model, and if this is the parameter of the non-model, then we can calculate the probability or likelihood, right? So, and so here I just give you a quick impression here. So if this is the case, we can use this non-model to calculate the p-value, the probability seeing a 6 straight heads like this. If this is a fair coin, the chance to get this data is like this. So this, if we use 0.05 as a cutoff, so what do you think? Given
No, the answer should be no. It's
yeah,
not.
definitely no. So you're gonna you don't believe like based on this data, you don't believe the null hypothesis is true, right? You're gonna reject it, and you believe there's a bias for this coin. Yes, very good, very good. Another example here. Oops. Okay, so suppose you do the same thing. Do the same thing, but instead of having a 6 straight heads, you got data like this. This is more reasonable, right? You got like 2 heads, 1 tail, 1 heads again, 1 tail, and let's see. So still based on the NUM model, which is like the p equals to 0.5. Then let's calculate the likelihood for this outcome. So the probability of seeing 6 heads and 2 tails equals to this. This is quite reasonable, right? So yeah, which means like, yeah, if your NUM model is true, if p equals to 0.5, then it is very likely to see data like this. So here we use our data to test our model parameter. Does that make sense? Cool. Okay, so I think for the theoretical part, I'm gonna stop here, and I'm gonna show you some R programming. Yeah, so every week I'm thinking about like maybe every week on Thursday after the lecture, I'm gonna give you some like simple, easy assignments. So for those practice, you need to use R, and so I'm gonna give you some like small tasks. When you go through those, when those assignments are not required, and I will not grade them, so it will not be accounted for towards they will not be counted towards your grade. But I think it's for your benefit, yeah, to practice those to help you understand and digest what we have learned in the lecture, and also by doing those, probably in the future, you can know how to use R to do coding or programming to help with your own research in the future. Yeah. Okay, so let me show you my screen for the R. Okay. So I'm still working on this, but oh no, this is not the right one. This is another project. Sorry. So far, any questions about today's topic, the binomial distribution, and how we do? So this is today we only use the binomial. But in the future, we're going to talk about different distribution, like the 2-sample t-test. That's something like the t-distribution, and also the chi-square distribution. They're the same. Even we use different type of distribution. The rationale, the theorem behind them is the same. So we are, to answer any question, no matter what kind of distribution you're going to use, based on your question, we can form 2 competing hypotheses. You put the easy one in the non-hypothesis, the difficult one on the other one, and you only test the non-hypothesis. So given the non-hypothesis, you have a non-distribution, non-model, right? So the thing is like, based on the non-distribution, or assuming the non-hypothesis is true, so you're going to use your data to calculate a test statistic and a p-value, and with the p-value, you can easily make a conclusion to answer your question. Yeah, that's the strategy, right? But today we focus on we only focus on the binomial distribution. So let me show you the sample question and the practice. I will. Geez, the same one. Too bad. I want to share this one actually. Let's see. I hope this one. Yes. Okay. Okay, so I'm still working on this. I'm just give you some idea of what I'm gonna give you. So if you have time over the weekend, yeah, just try. It takes about like maybe 5-10 minutes to go through everything. But if you are interested in that, so this can inspire you to do more search online. Because for example, if you want to know more about the binomial distribution, of course, Dr. Google is the best resource for you. All right, so here I will give you a address from which you can find some like R functions that are associated with the binomial. So for example, we have like 4 functions here. So for this 4, you can see like a binomial binom in each of those, right? So those 4 functions are or for the binomial distribution. But the first one is called the D binomial, which means like this one can help us to calculate the probability of any binomial random variable. So in this function, I'm going to show you what this 3 parameters mean. Okay, here, so this is a binomial, a single binomial random variable, and this variable actually came from an experiment. For example, if we toss the coin for 10 times, so that size means that how many trials did you do for the experiment? The size equals 10. And out of this 10, you only observed 2 heads coming up. So 2 success out of 10. And if for this model, the real parameter, the P, so the probability actually equals to the P hat. So if the real parameter for this binomial distribution is 0.6, which means the chance to have a head equals to 0.6. And then what is the likelihood you're gonna get, what is the probability density if you observed 2 heads out of this 10. So let's do this. So before I run this command line, can anyone tell me this probability would be a large one or small one? If the real probability of being successful is 0.6. So now if you do an experiment of size 10, you toss the coin 10 times independent, what's the probability for you to see only 2 heads coming up? Will this probability large or small?
Would it be big?
No, the other way, it's small, I think. So here the P equals to 0.6, right? Which means it's more likely to end up with a head, right? Okay, now if this is the case, if you toss the coin, this coin with the P equals to 0.6, 10 times. So by expectation, we expect to see more heads than tails. Do you agree? But in reality, if you only see 2 heads, which means, yeah, that's possible, but this outcome is very unlikely. So that's why you see the probability is only 0.01. Does that make sense? Okay, now if we change, so look at here, we still use this, but let's say if we put 7 here, what do you think? What's the probability for this one? Yeah, the big one. Look at here, the chance increased a lot, right? And okay, so if you can play this around a little bit, so it's fun. So if you put like 6 here, the probability is even higher, right? But if you look at here, so let's see, what's the chance to see 0 head? That should be very little, right? Does that make sense? Yeah, that's the probability for this specific data you observe. Okay, now this P binomial means like, okay, let me show you. This is the distribution density function. This is the density function or probability, and this is different based on the P equals to 0.6. So it's more likely to see 6 heads, right? The density will be high. But for 5 heads or 7 heads, you get lower, right? And so on. If you see the 0 heads, the probability is very low. So this is the probability density function. If you see all heads, yeah, also very low, right? Do you agree with this? And this function actually, the p binomial function actually here is, instead of calculating a specific density, it will calculate the probability and the curve either on the left-hand side or on the right-hand side. So we're going to talk about this next time, but I will leave this for you. You just look into this, do a little bit of practice, and try to figure out what these 4 functions mean. This one is to generate a random variable, binomial variable. Yeah, if the probability equals to 0.6. Just explore by yourself. And okay, so for this one, look at here. So here, if this is a fair coin, the p equals to 0.5, and if we toss the coin 10 times, so here 1 is not the same with this one. Here 1 equals to n, means how many binomial random variable you're going to generate, because this is to generate a single random variable. So if we have a fair coin and if we toss this coin for 10 times, what is the realized random variable can be generated from this distribution? So let me do this. So, oops. So I just generate this one from this distribution. So the p-value equals to 0.5, right? We toss the coin 10 times and it comes out like 6 out of this 10 are heads. That makes sense, right? That makes sense. If we do this again, let's do this again. Totally random. So this one, I toss the coin for another 10 times. Let's see what is S1. Oh, another 6. That's good. Sorry. Let me do this again. This time we got a 3. This is a random variable. 3 is possible, but it is less likely, right, to come out from this experiment. So this is what we do here. So if you keep doing this, you're going to see different phases. You see 4. So this is another realized value for this random variable, right? Okay. I think I'm gonna stop here. I still work on this assignment. I will post this practice to Canvas tomorrow. So if you have time over the weekend, you can give it a try. So I'm gonna use the rest of the time today, like till 11:15 or something. If you have questions for today, because at the beginning, for the first few weeks, I try to slow down, like a lot of very tough things. So, but later on, when we have successfully built up our foundation, so yeah, we could move very fast. Yeah, approaching the end of the quarter. So, any questions for today? Today, some big ideas here, like. So don't forget about, so we try to, for this week, we try to estimate R, right? We try to estimate R. So that R is the recombination probability or frequency between 2 loci. And when we have the data, we know how to estimate that R. So this is why here, look at here, we need to know how to derive the MLE, maximum likelihood estimation, for a binomial distribution given the data. So today I recorded that part, so to show you how we got the likelihood from the binomial distribution, And instead of dealing with the likelihood directly, we deal with the log likelihood. And we get the first derivative and set that guy equals to 0, solve that. That gives you the MLE, right? So the whole process is required. I could ask you how to derive this in the final exam. I will give you some example data in the final exam, and you're gonna derive this MLE and use that data to give me the estimate of this. Okay, so once we have this, so suppose based on your data, you got a estimation which is very close to 0.5. You want to know if this, this evidence is a real one or a fake one. So then you're gonna do the hypothesis testing, right? So this is what we're gonna learn next time. So once you have the estimation, so we need to know if this linkage, kind of linkage, right, between A and B is real or not. So we're gonna do the hypothesis testing. We're gonna test whether this guy equals to 0.5 or the observed this is a real one. And hopefully today, the two examples here, I can give you some idea about how we do the hypothesis testing and what is the theorem behind. Okay. So any questions? I can help. Is that clear? I like that. That's my favorite part. Every time, not for this class, and I also teach. I use this slides in my undergraduate genetic class. So it's very helpful. Yeah, they immediately students understand how we do the hypothesis testing. Yeah.
Mhm.
All right.
Thank you,
So
Dr. Jia.
I'm sorry.
Thank you.
Oh, sure, my pleasure. All right. So if you do not have any questions, Adrian. Oh, okay. So we're gonna stop a little bit earlier today. Yeah. Enjoy your weekend. So watch out the stuff I will upload to the Canvas. And if you have time over the weekend, yeah, just try it. Yeah. Okay. Bye everyone.
See you later.
See you on Tuesday. Bye bye.